Let's try to solve this problem here. A point charge Q1 is held stationary at the origin. A second charge Q2 is placed at point A, and the electric potential energy of the pair of charges is positive 5.4 times 10 to the power negative 8 joule. So let's try to illustrate the situation. Okay, so initially what we know is that the initial case involved Q1 being placed at held stationary at origin. So let's say this is the origin. Okay, I imagine here is the origin. Okay, then a second charge Q2 is placed at point A. So they didn't really specify where is point A, so let's just call this place as point A, and you place Q2 at point A. So let's say Q2 is placed over here. Then the electric potential of the pair of charges is positive 5.4 times 10 to the power negative 8. So like I said during lecture, we can imagine a pair of charges. In between all pair of charges, you can imagine them to have spring in between them. So we can think of it as if there's a spring in between them, which is either being stretched or being compressed. That's why there's potential energy stored in it. So in this case, the potential energy stored in it is positive 5.4 times 10 to the power negative 8. So U is positive 5.4 times 10 to the power of negative 8 joule. So this is the initial situation. You have Q1 and Q2 being spaced apart, and the potential energy is this value over here. When the second charge Q2 is moved to point B, so point B is another point which we don't know whether it's further away or it's nearer to Q1. I'm not sure. They didn't really specify it, but they say that the process to move Q2 from point A to point B involve the electric force doing this much work. Okay, so what it means is from the initial situation to the final situation, there will be work done by electric which amount to negative 1.9 times 10 to the power of negative 8 joule. Okay, so the process to go from initial to final state involve work done by electric by negative 1.9 times 10 to the power negative 8 joule. Okay, why do we know this one is work done by electric? Because they say electric force does this amount of work. So it's work done by electric force. Okay, so the final situation involved Q2 being moved from point A to point B, but they didn't mention Q1 is being moved. So we can draw the same origin. Okay, so Q1 is still remain at its initial position, but Q2 has been moved to another point, and we actually don't know whether point B is nearer or further away from Q1. Let's just simply assume, because they didn't really specify it. This diagram is just for our understanding. So let's say Q2 has been shifted from point A, which is slightly nearer, to point B, which is slightly further away. Okay, assume we are not saying that it is true. We are just for our understanding to see what has been moved. We simply put one point A and put one point B and say it has been shifted. Later, maybe we can come back to see whether our prediction is correct or not, where it goes further away, or whether it's supposed to be going nearer. Okay, we'll discuss that later. But for now, let's just simply assume that it moved from one place, which is called A, to another place, which is called B. Okay, so what is the electric potential energy of the pair of charges when the second charge is at point B? So now they are specifying that they want to focus on this situation because second charge is at point B. So this is the situation we are focusing now, and they want the electric potential energy of the pair of charges. So that means by for this pair of charges, which I'm going to imagine there's a spring in between them. So they're asking this U final, what is the value of this U final over here? Okay, so we'll try to solve this question again by seeing that the work done by electric over here can be related to the change in electric potential energy that occurs during this change from initial to final state. Okay, when you go from point A to point B, it involves the change of length of the spring, right? So you can imagine it being stretched further or being stretched less, or you can imagine it being compressed further or being compressed less. So the change in the compression or the stretch result in the change in the elastic potential energy of a spring, right? So in this case, you can think of it as the charge getting nearer or getting further away causes a change in the electric potential energy. And this change in electric potential energy can be related to the work done by electric force. So what do we learn in class? We learn in class that the work done by electric force, electric field, or work done by charge can be equals to negative delta U, where U is the electric potential energy. We have to be very clear where does the charge move from where to where. Okay, so in this case, it is Q2 being moved and it moves from point A to point B. So let's write clearly, this one is work done by electric for the charge to go from point A to point B. And to specify, that is Q2 that is moving, not Q1. Okay, so we can further break it open. We know that this delta here represents change, so it's always final minus initial. So for our case over here, the final will be B, because you go from A to B, A will be initial, B will be final. So you take final minus initial, that means you take final UB minus initial UA. Okay, B is the final situation, A is initial situation, so UB minus UA. Okay, so minus. Okay, so now you are asked to find UB, because UB is the U final, that's what you want to find. So you leave UB as it is. But UA, I think you are given the value. UA is this situation here, the electric potential energy when Q2 is at A. So this is the electric potential energy at that situation. So we can minus, then UA, we write down the value, which is positive 5.4 times 10 to the power of negative 8. So we have filled in everything for the right hand side. Let's move on to talk about the left hand side. The left hand side is work done by electric to go from A to B. We know the work done by electric is negative 1.9 times 10 to the power of negative 8. So we put it in negative 1.9 times 10 to the power of negative 8. Okay, so now you have plugged in every single value. What's left is just to determine the UB over here. So if you do your calculation, okay, I believe you get an answer of 7.3 times 10 to the power of negative 8 joule. Okay, yeah, so UB is equal to 7.3 times 10 to the power of negative 8 joule, and this is a positive value here. Okay, so that's our answer. So from our answer, we can actually check back whether A to B is further away or moving towards Q1. We can try to check. How do we check? Let's try to imagine it. Okay, UB, let's write it down clearly. We know that UA has a value of positive 5.4 times 10 to the power of negative 8 joule. Okay, we have UB, which is positive 7.3 times 10 to the power of negative 8 joule. So you can see that this process here involves an increase in U. Okay, let's don't use downward arrow, it might be a bit confusing. Okay, we know that this process going from A to B here involves an increase in U. So increase in U means I store more energy. How do we store more energy? We stretch a spring further, or we compress the spring further, right? Okay, so if it's a positive charge, then, or a negative charge, if it's same like charges, okay, this is situation 1. If Q1 and Q2 happens to be same or like charges, which is positive or negative, we should imagine them to be spring of infinite length, right? Okay, because they are initially spring that are very long, but it happens to be compressed. Okay, spring of infinite length. Okay, so spring of infinite length, if you want to store energy, you compress them. Okay, initially it was very long. To store energy, you want to compress it. Okay, so if you want to store more energy, in order to have increase in U, if you want to increase your potential energy further, you have to compress more. So compress more in this case means by gets nearer. Okay, so means by A to B is supposed to be a process of going from A to B will make Q1 and Q2 nearer. Okay, so in this case our diagram will be wrong if it's a positive positive or a negative negative charge. Okay, however, if it happens to be an opposite charge, which is either positive negative or a negative positive case, then we have to imagine it to be a spring which was initially zero length. Why spring initially zero length? Because you know that positive negative, they try to attract to each other. So if you don't disturb them, they're supposed to be as close to each other as possible. So if you want to distance them apart, the process is actually you stretching it apart. Imagine if you are stretching a spring that was initially very short, you stretch it to be longer. That's the same idea as taking a positive negative charge which are supposed to be near to each other, you stretch them apart. Okay, so this spring of zero length, initially, if you want to increase the electric potential energy, what should you do? You should stretch more. Okay, stretch more. So you can say process of going from A to B will make Q1 and Q2 get further apart. Okay, let me rephrase what I write up there, or else it might be a bit confusing. Okay, you can write it as A to B will makes Q1 and Q2 gets nearer. Okay, so what does it mean? It means that if today Q1 and Q2 happens to be like charges, Q1 positive, Q2 negative, or Q1 positive, Q2 positive, or Q1 negative, Q2 negative, if they are like charges, what happens is if you want to increase your electric potential energy, you have to compress the spring more, because the spring was initially infinite length. To store energy, you want to compress it. To store more energy, you compress it more. So to compress it more means by you have to bring the two charges to get nearer to each other. So the process of going from A to B is actually making Q1 and Q2 nearer to each other, which in this case, this diagram is incorrect. If they are like charges, this diagram is incorrect. B is supposed to be nearer to Q1 compared to A. Okay, but if you are in situation 2, which Q1 is positive, Q2 is negative, or Q1 is negative, Q2 is positive, they are opposite charges. In this case, they want to get close to each other, right? You can imagine them to be a spring of zero length initially. Initially, they are close to each other because they want to get close to each other. But if you want to store energy, it means you want to stretch the spring to store energy, right? So that means you bring the charge more further apart. The more further apart these two charges are, the more energy that you store. So you want to stretch it more, means you want to make them more further apart. In that case, if you want to increase the electric potential energy stored in this pair of charges, you want to move from A to B in a way that you make Q1 and Q2 get further apart, then you store more energy. So in this case, this diagram here will be correct. Moving the Q2 from A to B, you make the distance between Q1 and Q2 gets further away, then you store more energy if they are opposite charges. Okay, so I usually relate electric potential energy to elastic potential energy. So if you are unclear how they are related to each other, you can probably refer back to the lecture we have. Okay, so that's it for this question. Thank you very much.